All right, last video for today. Going back to this isoparametric map. For 2D, again, we have a parent domain with the coordinates xi and eta, which I'm gonna call xi vector. And then we have the physical domain, in this case for the reference configuration, x1, x2, which is in the x vector. And the isoparametric map basically just means that if we have some shape functions associated with the nodes on the parent domain, then the sum of the shape functions times the coordinates of the nodes will give us a way of interpolating any point here to any point here, right? So basically that's what the isoparametric map does. It will tell us how to go from some point xi star to some point x star. But like I said before, typically we want to take derivatives, so the thing that we need to introduce is the Jacobian. So the Jacobian is the Jacobian of the map. So again, the isoparametric map is, so this is the isoparametric map. X equals sum of x vector equals sum of the basis functions, which are in terms of the xi vector, times the coordinates xie, right? Where, each of these, so these are scalar, obviously the functions are scalar, so these are scalar functions, scalar valued functions. They take in a vector because again, if you have this is the xi 1, xi 2, or xi and eta, and this is the quadrilateral, right? And you can have 4 nodes or 8 nodes. So this is the x1, x2 space. So a point here would be a point xi, and a point here would be a point x. And the nodal coordinates, so the nodal coordinates, for example, for the linear quadrilateral, we're going to have 4. So these are vector x1 of the element, but do not confuse x1, the entry x1, with the coordinate x1 of the nodes. So x2 of the element, x3 of the element, right, and x4 of the element. So for the linear quadrilateral, for example. But do not confuse, so careful, x1 without the vector, that's just the coordinate. Same as x2, that's just the coordinate. Whereas x vector 1e, which has basically the x1 component, maybe I should use x11e. So the one component of the x component, you can think of this as the x component of the coordinate, and the y component of, maybe I should do, I don't know how to do it so that it's not super confusing. Does that make sense? Basically, I don't know, this seems very confusing. I'm gonna revert back to x and y just because, so this will be, maybe I should use the uppercase. Well, I'll just keep it like it is. But, this will be x and y component of the first node of the element, right? It's just that in the general case, I don't use x and y, I use x1 and x2. So this will be x11 in a way and y11. So x component of first coordinate component of the of the location of the first node, y component or second component of the vector of the first node. Does that make sense? Hopefully. Yeah, so just be careful. Maybe I'll change the notation a little bit, so that it's not super confusing. Because this I is not the coordinate, is the node. Well, I'll just move on. Okay, so that is the map. This is the map, right? So what is the Jacobian of the map? What we want is basically the partial derivative of x with respect to xi. Right? So we are going to find this, we're going to call this Jacobian, the Jacobian of the element. And again, also don't confuse this Jacobian with the determinant of the deformation gradient. I know we are using the same letter, but hopefully in the book, for example, they put this E just to make sure that you associate this with some element operation. I'm not sure I'm gonna do that. I'm just gonna keep using J, and then we just have to be careful between this and the determinant of F. So that's another one that you should be careful with. This is not the determinant of F. All right, so this means taking the derivative of the isoparametric map, right? So this is just taking the derivative of the isoparametric map, which is the sum of the shape functions times the vectors for each of the nodes. And we can put the derivative into the integral, and then what this will be is, I'll explain it in index notation, but this is essentially xi dyadic product of the, well, and this is a sum, so I keep the sum outside, sum over the nodes, maybe I should do that, number of nodes. So then that it will be clear that this I is the number of nodes and not the coordinate 1 or 2. Of dni dxi with respect to the xi. And that's it. We can call this is basically the shape functions which we will have in terms of the coordinates xi, which are either xi1, xi2, or xi eta, whatever the name. So this is basically the gradient with respect to the xi coordinates of the shape functions, right? And so here we repeat the I from I equals to 1 to the number of nodes of the vectors of the coordinates of the nodes dyadic product with the gradient of the shape functions with respect to the xi coordinates. So that's it. That is the Jacobian. If you are curious as to why do I have this dyadic product here, let me just do a note here. Note in index notation, the derivative of x with respect to xi vector would be a matrix, right? That has, and now these are really the components. So this would be, let me use A and B so that we don't confuse with the other I that I introduced. So this would be, in 2D, this would be a matrix of the yeah, I will need definitely an extra page. So this would be a matrix where this entry would be x1 and x1, not x1 the vector x1, but the coordinate x1 with 1, x1 with 2, x2 with 1, x2 with 2. Actually, let me move this down here. So this is technically what it is. So let me just do use x1 as x, x2 as y, xi1 as xi, and xi2 as eta. And then basically what I want is, hopefully this makes it a little bit less confusing so that you don't have to worry about, obviously there's two indices here, so that's why it's convenient to not name the coordinates with just 1 or 2. But if you are getting confused with whether this one has anything to do with this one, which they don't, because one is related to the node and the other one is related to the coordinate. So if I replace x1 by x, x2 by y, xi1 by xi, xi2 by eta, then this will be basically derivative of the x coordinate with respect to the xi, derivative of the x coordinate with respect to eta, derivative of the y coordinate with respect to xi, derivative of the y coordinate with respect to eta. Same thing. It's just with the, instead of using the index notation, I'm using x, y, and then xi eta. And I can expand this a little more. So I'm gonna get this matrix. So this matrix, as I said, is equal to this. Right, and then the sum of the xi component, now these xi vectors, those are the xy coordinates of the node I. So that's why also I'm using a and b here. So if you recall, this is basically, let's see what this is. The derivative of the x with respect to xi, that just means the derivative of the one, so the isoparametric map is this guy, right? So let me rewrite the isoparametric map then. So the isoparametric map that I put before was x equals sum of I from 1 to the number of nodes, shape functions, which are a function of the xi vector times the x vector of the node, right? So this will give you two coordinates, right? This will give you x1 coordinate and x2 coordinate, which I'm calling basically the same as the x and the y coordinate. So this is, I don't like this one because typically I refer to things with coordinates with indices. So obviously here there's no index, right? There's no 1 and 2. So I don't particularly like this, but it might make it clearer. Actually, let me move this a little bit to the side for a sec. I'll bring it back. So this will be, obviously the first one would be the sum of the shape functions, which are functions of xi and eta, and also here, times the, now here again, xi e1. So the x component of the I node and the xi2e. So this will be the y component of the ith node, because I is from 1 to the nodes, number of nodes. So if you think of this basically the same, I'm just renaming it so that it's clear. Again, just want to be absolutely clear that you don't confuse x and let me do the proper xi and yi. Right, so the isoparametric map here, it's a 2 to 2 map. So I will plug in vectors xi, so basically components of xi and eta, to evaluate the shape functions. And then I'm gonna get back the two components, right? So I'm gonna get back a vector x, which is made out of two components. And so hopefully this makes it clear that the I here relates to the nodes. And then these 1 and 2, I use A for that, right? So this A would be 1 and 2. And so this will be the map, and the Jacobian, which I want, as I explained here, this guy, right? This xi vector, the x vector, the xi vector, is going to be the derivative of this. So basically you can think of either this one or this one or this one. I mean, they are all the same. Hopefully that's okay, right? So for here, I need the sum of, and now here I need the partial derivative of the ith basis function with respect to the xi1 times xie1, and I is from 1 to the nodes. I'm going back to A and B, to basically this guy. So let me just sum this. Here I have some of the shape functions derivative with respect to xi2. And then here I'm gonna have, on the bottom is the same, but now I have the y component. So this is basically the xa d xi b. Hopefully this is clear. This is the and you could rewrite it with just replace x1 with x's, x2 with y's, xi1 with xi's, and xi2 with etas. I'll just do it for completeness. I might need to squish this a little bit. Running out of space. Let me also shrink this a little bit. All right. So let's do that. So here, what I was saying is that replace this. I don't need the 1. I don't need the 1 here. Here instead of xi2, I'm gonna do eta. Here instead of 1, and here I'm gonna do y. And here I'm also gonna do y and eta. So hopefully that made sense. And again, my whole point is to try to unpack a little bit better what this is, and I feel like it might be useful to think of it in terms of x, y, and xi eta, and not just xa and xi b. That's why I'm doing this. All right, so that is the Jacobian. Clearly we can compute the Jacobian, right? Because we have the shape functions, ideally. I haven't given you any shape functions, but ideally you have the shape functions. And so you can take derivatives of the shape functions with respect to the xi eta, right? Because I'm going to give you the shape functions with respect to xi eta, you can take derivatives. And then basically what I'm saying is you need those derivatives and you need the coordinates of the nodes. That's it. If you have the coordinates of the nodes and you can evaluate the shape functions and the derivatives, you can compute both the isoparametric map, so basically the map between the xi and the x, and you can also compute the Jacobian, right? And you can see that this expression that I have right here is the same as doing the outer product of and we can see why this is the outer product, because yeah, I was going to do it in index notation. So let me do it in index notation so that you can see that is the outer product. So I want dx dxi, right? And in index notation, I said this is dxa with respect to dxi b, which would be the partial derivative with respect to xi b of the sum from I equals to 1 to the number of nodes of the shape function I in terms of xi times the x. So now here, if I want the a component, so here I will have this xi a, where a refers to the I refers to the node, a refers to the component. So I have that, and so this is, note that the a, so for this tensor, and this is a second order tensor, right? Because we have, well, or a matrix at least, because we have a and b indices. So this will be this guy, well, sum of x node I component coordinate a times the only thing that depends on the xi b is this. So this is the bth component of the gradient of the shape function I, right? So you can see that this comes from, basically this is the row and this is the column, and these are two, I'm getting components from two different vectors. So I'm getting the first component from the vector of the xi, so the nodal coordinates, and I'm getting the second component from the gradient component, so from the gradient of the shape function. So this is why when I go back to matrix notation or tensor notation, here I'm gonna get, this is just gonna be the xie vectors, or sum of the xie vectors with the gradients of, with respect to xi, of the shape functions. That's why we get this outer product. Hopefully that made sense. So they are all the same as I equals to 1 to the number of nodes. So all of these are the same. This is the same, this is the same, this is the same, this is just one of the components. If you want the matrix, this is the same. So I just rewrote everything a ton of times, making it super confusing, but hopefully not extremely confusing, just a little bit. All right, so that is the Jacobian. And so what can we do with the Jacobian? We can do the same thing that we did for the 1D case, which is we can take derivatives with respect to x right? Even though we don't have explicit shape functions in terms of x. So I need one more here. Oh, actually, this is good. I have a subtitle for what I want to do next. Yeah, so now think back again. We have the space, which is either xi1, xi2, and we have some quadrilateral in the space x1 and x2, right? And we have a map that takes us from here to here. Is the isoparametric map. Where basically we have a few nodes here. Doesn't have to be 4. Could be 9. Depends on the element, right? We have a bunch of nodes. So these nodal coordinates, this is what I call xie vector. So that would be the nodal coordinates. And they correspond to a point here, which has an associated shape function. Associated point in the parent domain and associated shape function NIE, but it's in terms of the xi eta coordinates. So we have that. Now, obviously, as I said, the isoparametric map relates the x coordinates to the xi coordinates. But what if we have some field? Let's say we have some values associated with the nodes for some other field. Let's say we have thie, which are values of, for example, values of some field, scalar field. At nodes. Could be temperature, for example. So for every node, we have a value of temperature. And so what we can do is we can use the same shape functions to interpolate this. So we can basically sort of think of the value of the temperature and copy that here, right? So we can sort of like copy this value here. And then what we can get is theta, a function theta of the element, which is explicitly a function of xi, right? Because we can write it as, again, the sum of the shape functions, which are a function of xi, times the temperature values. So what we are doing now is we are sort of like mapping now these nodal values to every node here, right? And then because we can use the shape functions that we have in the parent domain, we can interpolate theta in this domain. So let's say that we can interpolate it, some way like this. Let's say that it looks something like this, right? So we can interpolate this theta field given just the nodal values. Because I can sort of just transform those. This is very similar. This should look very similar to what we have been doing with kinematics, where we can always map some scalar field from one set of coordinates to another set of coordinates, right? So here explicitly we can define it in terms of the xi. Now we have a map between the xi and x, right? So even though we cannot explicitly write the theta in terms of x, you could always get a contour plot of the corresponding. You could always get this contour plot even though you don't have the theta field directly in terms of x and y, you can still do this because you can always, and this is basically what you have been doing in your homework, you can always do and say, evaluate at psi and eta, you can evaluate the corresponding x let me just do here. So to get contour of theta in x space, you would evaluate, you only have the explicit representation of this theta in terms of the xi. So you would evaluate at a particular xi star, whatever point, right? Whatever point xi star. And you can evaluate the isoparametric map, and you can get the corresponding x star. You can also evaluate the corresponding theta star, right? Just evaluate this map. And then just basically all you will need to do is take these two and then plot theta star on the x star, right? So given that you can interpolate things here, all that you need to do in order to visualize this contour will be for every point that you evaluate here, get the corresponding point that it goes to, and then just plot the value of the temperature at that point. And that way, even though the shape functions are only defined in the parent domain, you could always go and plot it here. And so this is basically what you have been doing with for the kinematics part, because this is essentially like a kinematics problem, right? It's just that we are using this parent domain that has nothing to do with a deformation. So before, when we have been introducing the deformation map, and the deformation gradient is always in the physical space, so it's always from some starting point of a body to how it gets deformed. We are doing kind of a similar thing, but from an arbitrary nice domain. And this is just because it's useful to, this nice domain is useful to define the shape functions. And then we can use those shape functions to interpolate things in this physical domain. So that's how you would evaluate the contour in the x space, even though you can only have functions in terms of xi. Similarly, you can see that you can easily get gradients in the xi space, right? So you can easily say so easy to get gradients in xi space. Again, because we have the shape functions in terms of the xi space. So you can always get gradient with respect to the xi variables of the theta e, because that will just require the sum of theta e times the gradient of the shape functions with respect to the xi coordinates. So this is very easy. Now, but usually you don't want this. Like, we don't want this. Right? So typically what we want is we want to take gradients in the x space. We would like to know the gradient of theta in the x space. But you just need to use chain rule. So what if I want, what if I want the gradient with respect to x of theta e? Well, then I need to use the chain rule. So then I cannot do, I still have the sum of from 1 to the number of nodes, but now I'm not going to take derivative of just of the shape functions with respect to xi, but I need to do chain rule. So I need to take derivative of that with respect to the x's. So this is what I need, right? Chain rule. And this, in particular, this matrix right here, this dxi dx, this is the inverse of the Jacobian. Because, you know, the Jacobian that we have here is, where did I put it? Is the derivative of x with respect to xi. So here we have the derivative of xi with respect to x. So that is the inverse of the Jacobian matrix. So, and this is obviously, this is the gradient of the shape functions with respect to the xi still. So I still can take derivatives of the shape functions with respect to xi, and then I just need to post multiply with the inverse of the Jacobian. And now this is a matrix, so this Jacobian is a 2x2 matrix or a tensor. It is actually also a tensor, I guess, within this domain. And this is a vector, right? This gradient of the shape functions with respect to xi. So this is sort of a matrix vector multiplication. So if you think of it in terms of index, we want the gradient with respect to x of theta e, which means we want the partial of theta e with respect to x a. And so that is going to be the sum from I equals to 1 to the number of nodes of theta I e, and then partial of shape functions with respect to xi b, and then d xi b dx a. So that's what we want. Here you can see that this is a vector, right? This is the gradient, this is the inverse of the Jacobian, so this is J inverse, this is the gradient of the shape functions with respect to xi. And so this, this is a second order tensor or a matrix multiplying a vector, but it kind of looks awkward because the vector is on the right, you are contracting. Notice that you are contracting. This is sort of like the transpose of a vector multiplying a matrix on the left. So we can just rearrange this a little bit and do basically well, for now, let me just move this a little bit and it will become clear. So this is, again, like this, but now I'm gonna do this. I'm gonna do dxi b dxa times dni with respect to dxi b. So this almost looks like matrix vector multiplication, right? So again, this is the Jacobian inverse. And this is basically the gradient of the shape functions with respect to xi. And it's not your standard matrix vector, because the one that is being multiplied is the first one here. So I need the Jacobian transpose in order for it to be correct, right? So that means that this will be, I mean, this is all correct. This is all is correct. I'm just trying to find a way of bringing it back to sort of matrix algebra or tensor algebra. So this is going to be the sum from I equals 1 to the number of nodes of theta IE, and now J minus transpose times the gradient with respect to xi of the shape function I. So now this makes sense, because when you transpose this, you can do the standard matrix vector operation, right? It's just that here it's not quite there, because you have a matrix with entries BA multiplying something with entry B. So that's it. Yeah, so this is the way you can get gradients with respect to x. Again, in practice, you're taking gradients with respect to x without ever computing the inverse map, the inverse of the isoparametric map. It's more like the same thing that I was explaining for 1D is basically in practice you have, because you only have things defined explicitly in terms of the xi. So in practice is pick a point xi star, right? Evaluate the corresponding x star, evaluate the corresponding Jacobian at xi star, so this is just basically evaluate the isoparametric map and the Jacobian. You can evaluate also theta E, right, at xi star. Again, this, all you need to use in this part are the shape functions and maybe the derivatives of the shape functions with respect to xi. So all of those you should have. So you have that. From here you need to get the inverse or the transpose inverse of the Jacobian, right? Here you can also get the gradients of the shape functions with respect to the xi at xi star. And maybe I should also make a note here. So actually this guy right here, this is nothing but the gradients of the shape functions with respect to x. So actually let me move this to down. So with these two, you can get essentially the gradient of the shape function with respect to x. And now with that you can also evaluate the, you don't even need to evaluate the theta E. But once you have gradients with respect to of the shape function with respect to x, you can also use that to compute, so this to compute gradient of theta with respect to x, because this is nothing more than, maybe I should add it here, this is nothing more than the sum of I equals 1 to the number of nodes theta IE times the gradient of the shape functions with respect to x. Even though the shape functions are directly a function of xi, you can get the gradient with respect to x. Yes. So yeah, so that's how you compute gradients with respect to x, even though you only have functions and derivatives directly with respect to the xi coordinates. All right, so I think that's, oh, okay, the last one that I want to do for this class, I guess I wanted to do also the deformation gradient. Okay, so this is, let me just do one more. So this was basically for a scalar field. So what if I want a vector field? What about vector field? So for vector field, let's say you have a vector field u, which we're going to explicitly have in terms of the psi, right? So this is going to be the sum of the shape functions, which are in terms of psi, times now the nodal, again, this is I equals 1 to the number of nodes, right? So now these u are some displacement, oh, could be any vector field. Like u is some vector field that we want to interpolate. And so UIE are the values of the vector field at the nodes. And so now what we want is we want the gradient with respect to x for this u. And again, this is going to be the sum of the I equals 1 to number of nodes of u IE dyadic with the gradient with respect to x of the shape functions. So that's, yeah, it's nothing more than the, oh, as long as you can calculate this gradient, which I just show you up here how you calculate the gradients of the shape functions with respect to x, then the gradient of the vector field is just, yeah, the components of the vector field at the nodes dyadic with the gradients of the shape functions, because this is very similar to what we were doing actually for the Jacobian, right? So where did I put the Jacobian? Right, so this is basically the same thing that I was doing here, but in the Jacobian, remember that I was taking derivatives with respect to psi. So I wanted the gradient with respect to psi. So now I'm just doing gradient of a vector field, but if I want the gradient with respect to x, I just need, yeah, the sum of the nodal values, dyadic product, and then this is the same as before. So let me just write it and delete it. So if I wanted the gradient of the vector field with respect to the psi coordinates, but I mean, I'll leave it, but it's not. This is, oh, you don't really compute this one. Because you never really use gradients with respect to psi coordinates, but basically, if you wanted to get the gradient with respect to the psi coordinates, all you would need to do would be similar structure, but with the gradient with respect to psi, right? Which is what we did before. So for this one, you don't really need to do anything special, because the shape functions are directly in terms of psi. So taking gradients with respect to psi is just standard, right? So this one, if you wanted to take a gradient with respect to psi of a vector field, you could do it. But what we are mostly interested in is basically taking gradients with respect to x. And this is the same idea. Hopefully this, even the contour plot that I have here makes a lot of sense. That even though you have everything defined here, because you have the isoparametric map, you can still plot things in the physical domain and therefore also get, gradients in the physical domain. So that's the same idea, and it's just from scalar here to vector here. All right, so I'll stop right there because I think it's already a lot of information, and I'm going to introduce the quadrilateral shape functions in a different video. I don't know if I'll make a video. I think I might just code it in Python. And then if there's some questions, I'll make a video. But otherwise, there's a lot of video content already for today. So I think I'll stop there. And then hopefully the rest, just like the specific shape functions, I'll just show you that I have in the rest of the nodes, I actually will introduce the shape functions for the quadrilateral elements. So this is just so that you have an explicit expression for the shape functions. But the concept, I feel like the concept should be fine right now. So the only thing that we're lacking is essentially this, right? How do the shape functions look like? And so here, for example, for the linear quadrilateral element. So I think I'm not gonna make a video, and I think I'm just gonna code it. I'm just gonna code this linear quadrilateral, these 4 shape functions, and then hopefully that one, if you just go through the notes and go in the book, you can find also the list of the shape functions for the linear quadrilateral and make sense of the Python notebook. And I think I'll just stop with the explanations here. I think in terms of derivations, as long as you get this part, this applies to basically any sort of shape functions. What I just derived, it applies to any shape function. So to any element. The only thing that I need to introduce specifically to an element would be the actual shape functions, right? So just need to define specific shape functions. And so for the moment, I'm not going to make a video about that. I'm just going to upload this one and I'm